Friday. Joy! Okay, so exam 3 is on Friday. The topics, there's no column buckling. But it's everything before that. So be ready for statically indeterminate systems, elongation, angle of twist, deflection, all that kind of stuff, okay? So I wanted to do an example problem with deflection where there is a change in the bending moment function. So let's go with, so let's say that there is a fixed joint over on this side and a pin joint on this side. Let's say that a bunch of stuff happens at the center. Let's say that there is a 5,000 Newton force and a couple of 200 Newton meters, and then a downward force of 1,000 newtons. And let's say this is 1 meter and this is 1 meter. We're going to neglect the weight. And we're going to do a calculation of a stress tensor at this point. And let's say that this has, what could we do here? Let's do a, we'll see how far we can get on this, but let's say that this thing has a thin-walled rectangular cross-section where the thickness is equal to 2 millimeters. And this is 4 centimeters. And this is 8 centimeters. And let's say that we want to calculate the stress tensor here. Okay.
Does it matter how high it is from the center? Yes.
How high it is? Yes, it's halfway. That's right. And okay, I'm getting too fancy because this, I'm sorry, you're going to have to erase some of this. Forget about the angle of twist. That is just not going to happen here. So let's calculate it along this line. Okay. So
is it solid now?
It's solid now, yeah. It's so easy up here to design engineering systems. Okay, so what are we going to do first? We got to calculate that stress tensor. Yeah, so first we're going to do the statics. That's where we're going to find out that this is statically indeterminate. So free body diagram of the whole thing. Anytime someone asks you the first step, free body diagram is a pretty good way to go, even if you haven't even been paying attention. So we got this guy over here. Call that RA. We have the 5,000 at the center and the 1,000 down. And then over here, we have RB, and we also have a reaction couple. I'll call that MB. Bless you. And so Newton's second law says RAX, RAY plus negative 5,000, negative 1,000 plus RBX, RBY is equal to 0. So from that we get two equations. The first one says RAX plus RBX is equal to 5,000. And the second one says RAY plus RBY is equal to 1,000. And then the moment equation about the z-axis. We have a clockwise moment. So this is my about point. We have a clockwise moment with a moment arm of 1 and a force of 1,000. So that's negative 1,000 plus mb plus a counterclockwise moment with a moment arm of 2 and a force magnitude of rby. So plus 2rby. And that's equal to 0. And that gives us our third equation that says 2rby plus mb is equal to 1,000. In a statically determinate problem, now you could solve this for the external loads, but here we can't. We have 3 equations for 1, 2, 3, 4, 5 variables. So now that we've done the statics, we've seen that it's statically indeterminate. What's the next step?
Cut 1.
Yes. So cut 1. This is valid for x's between 0 and 1. We have the force RA. We haven't made it to the stuff at the middle yet. Remember, we're neglecting the weight. We don't have any distributed loads. And so the only other things we have are the internal loads, T, V, and M. And Newton's second law says RAX, RAY plus T negative V is equal to zeros. So T is equal to negative RAX. and V is equal to RAY. And then the moment equation about the z-axis again. My about point is over here. And so all we have is m minus vx is equal to 0. So m is equal to vx, which is RAY times x. Okay? So that's on the first cut. And I'm not counting these in my numbered equations. We're just going to use these when we go to the total elongation and the total deflection. Okay. And now we'll go to cut 2. This is for x values between 1 and 2. So we have RA. And now we have a 5,000 Newton force there and a downward 1,000 Newton force, and then the internal loads. Newton's second law says RAX, RAY plus negative 5,000, negative 1,000 plus T negative V is equal to zeros. And so from the x equation, we get that T is equal to negative RAX plus 5,000. And V is equal to positive RAY minus 1,000. And then the moment equation we have a moment arm of 1 for this clockwise moment produced by the 1,000. So that's negative 1,000 plus m minus Vx is equal to 0. So m is equal to Vx plus 1,000. And so m is equal to RAY times x minus 1,000 times x plus 1,000. Okay, so now we have all our internal loads expressed as functions of the external loads. Why does it help to come up with the internal loads as functions of the external loads? Like where are we going with this?
When we calculate the stress tensor.
Yeah, but actually we're not there yet. The reason we're doing this is just simply because we've started this system of equations with the statics. And the variables that we have in those equations are external loads, okay? When we go to our calculations for elongation and deflection and stuff, those are all in terms of the internal loads, right? Mm-hmm. Well, we don't want to introduce, we could just leave those as T, V, and M, and then a T, V, and M representing the other part. But then we'd be introducing more variables into our equations. So we want to boil everything down to relationships with those external loads because we've already put those in equations that we need. Okay? Eventually, we're just going to have this big system of equations that we have to solve. Okay? So our next step, now that we have the internal loads in terms of the external loads, is now we want to use those expressions to calculate the total elongation and the total deflection. Okay? And then those are gonna give us our extra equations to solve this big system. Anybody have any questions about that? I think, with this kind of stuff, it's really important to just keep your eye kind of on how all these pieces are gonna fit together. Otherwise, it's so easy to get lost in the infinitely many steps of algebra, Okay, so let's start with the elongation. So the total elongation, I'll call it delta, is equal to the internal tension of the first piece times the length of the first piece divided by, well, I guess we're not even going to need these, but divided by E times A of the first piece, plus all that same stuff for the second piece. And since the motion is eliminated at both ends, we know that this has to add up to be 0. Okay, so on the first piece, it's 1 meter long, and we have our internal tension is negative RAX. So negative RAX times 1 meter divided by, I'll just leave these as E times A, plus the internal tension on the second piece, so that's negative RAX plus 1,000 times the length of the second piece divided by EA is equal to 0.
Did we have the 5,000 or the 1,000 being extra?
Yeah, yep, you're right.
5,000.
Thank you. Okay, multiply both sides by EA, and you get RAX negative minus another RAX plus 5,000 is equal to 0. So you can write this as 2 RAX is equal to 5,000. Okay, that is our fourth equation. I mean, this actually lets us solve for this, but let's deal with all that stuff at the end. So this is our fourth equation. Okay. And now we go to the part that's sort of painful, the deflection. Deflection is always a hassle in statically indeterminate structures. So how many additional equations do we need? Remember that we're going to have constants of integration from the deflection.
Okay, so 3, correct?
So this time we need one more because we have 4 equations now for 5 variables. And then the additional variables that are going to come up, if I'm thinking about this right, are 2 constants of integration on the left half and 2 different constants of integration on the right half. So we need 5 more equations. Okay? And we're going to have 4 more variables. Don't look at me like that.
Isn't C, because we're usually,
I didn't make the rules.
I'm thinking in my head, C1 and C2 are going to be equal to 0, and that would be.
Oh, yeah. But those are going to be equations, you know.
Yeah,
I'm going to just
in
put
my
those
mind-
all in our big system. Okay, yeah.
I count them as zeros.
Yeah. Okay, that's right. So the stuff that happens when x is equal to 0, that's going to be really easy with the math. Well, let's get into it. So the total deflection, we have that at every x, E I V double prime is equal to the bending moment. And so where are we going to know stuff? We know that, so our boundary conditions are going to be, first, the deflection at x equals 0 is going to be 0. Do we know anything about the slope of the deflection at x equals 0?
No.
No. That pin joint says that the angle of that thing can be any angle. The pin doesn't restrict that. Then what about at the fixed joint? Well, that's at x equals 2, and the deflection has to be 0. At a fixed joint, does the slope of the deflection, is it restricted?
Yes.
Yeah, so that also has to be 0. So v prime at 2 is equal to 0. And now we need 2 more. What are those going to be?
Is it deflection of 1 equals deflection of 1?
Yes, exactly. So that's at the seam, the place where you change cuts. The deflection of the left has to equal deflection of the right, and the slope has to equal. So I'm going to write that as V using using cut 1. Well, maybe I'll write that as, so the deflection using cut 1 at x equals 1 has to equal the deflection from cut 2 at x equals 1.
So you can subscript all of these if you want to.
All of what? Oh, yeah, you're right. You're right. Yep. That probably is helpful. So that's 1, that's 2, that's 2, and the subscripts here are just saying which internal load functions we're using for each of these. Okay. Ooh, I'm going to do that in every class from now on. And then V1 prime has to equal V2 prime at x equals 1. Okay, that's a lot. So first we'll do the deflection. Well, let's just do, for cut 1, we'll come up with the functions. So we have that E I V double prime is equal to our bending moment function from cut 1. That's RAY times X. Integrate once, and you get EIV prime is equal to RAY over 2 times X squared plus C1. Integrate again, and you get EIV is equal to RAY over 6 X cubed plus C1X plus C2. Okay? And now our boundary condition that says deflection using the first cut when x is equal to 0, that's just equal to C2, and that has to be equal to 0. So our fifth equation says C2 is equal to 0. That's not much of an equation, but it's easy to use. And now we'll go to cut 2. We have that EIV double prime is equal to, now we'll go to, so our bending moment function is this one. So that's RAY times X minus 1,000 X plus 1,000. Is that what it was? Yes. Integrate once. So you got RAY over 2 X squared minus 500 X squared plus 1,000 X plus C3, and integrate again. EI times deflection is equal to RAY over 6 X cubed minus, that would be 166.6 repeating X cubed plus 500X plus C3, 500X squared, sorry, plus C3X plus C4. And now we'll go to our boundary condition that says, well, let's first use, okay, so EI V2 at, no, V cut 2 at 2 is equal to 0. So we have 4/3 RAY minus 1333.3 repeating plus 2,000 plus 2C3 plus C4 is equal to 0. And so that's 1.3 repeating RAY plus 2C3 plus C4 is equal to negative 666.6 repeating. And this is equation 6. And now we'll use the requirement that V prime using cut 2 evaluated at x equals 2 is equal to 0. We have this expression for EI V prime. So one thing I didn't mention, I shouldn't gloss over this, is notice that I'm actually not using like the deflection is equal to 0 and the deflection prime is equal to 0. I'm using EI times the deflection and EI times deflection prime is equal to 0. That works fine because it's 0. It would not work if you had a value that said at this point the deflection is equal to negative 2 centimeters or something. Are you with me on that? I mean, anything that you're setting to 0, you can set EI times that thing to 0. So that's what I'm doing. Okay, so RAY over 2 times 4, so that's 2 RAY. Minus 2,000 plus 2,000 plus C3 is equal to 0. And so our seventh equation says 2RAY plus C3 is equal to 0. Okay? Now we have two more equations, and those are going to come at the place where the cut changes, so the functions change. And we have to have matching there. We have to have matching of deflection so that it's continuous, and we have to have matching of the slope so it doesn't have like a cusp there or anything, okay? So it has to be smooth at that point. Okay, so now we're going to say deflection using cut 1 at an x value of 1 is equal to deflection using cut 2 at an x value of 1. Using cut 1, we have RAY over 6 plus C1 plus C2. So RAY over 6 plus C1 plus C2 is equal to, now using the second function, RAY over 6 RAY over 6 plus 333.3 repeating plus C3 plus C4. These two cancel, and we get an eighth equation that says C1 plus C2 minus C3 minus C4 is equal to 333.3 repeating. And then the last one we're going to use says that the slopes have to match. So using the first cut, V1 prime at 1 has to be equal to V prime using the second cut at 1. And where is that? So cut 1, we have RAY over 2 plus C1 is equal to, now using the second cut, RAY over 2 plus 500 plus C3 and so our ninth equation, these cancel, and you get C1 minus C3 is equal to 500. And so now we have 9 equations for 9 variables. Some of those are pretty trivial, but I'm just going to do it as a matrix.
Wait, that's a question.
Oh, yes. In the 8th equation, so that came from That's the deflection, and so that was the 500 minus the 166. Yep. Okay, and 9, so. Okay, so the equations: 1, 2, 3, 4, 5, 6, 7, 8, 9. And the variables are R, A, X, R, A, Y. R, we do have BX and stuff in there, right? Yes. RBX, RBY, MB, and then C1, C2, C3, C4, and then the constants. Okay, can someone do me a favor and scroll back through these and just read me the coefficients? So go back to equation 1 and just say like, RAX, we have 1, RBX, we have 1, 5, constant 5,000.
I didn't write all of them down.
Oh, okay.
I missed a couple of
That,
ones.
yeah. Oh, okay. Okay.
Sorry, we're back on.
I thought you just had a place on your page where you're just like a bunch of math.
Equation 1,
Okay.
RAX is 1,
Yep.
RBX is 1.
Yeah.
Constant 1.
Okay.
2, RAY is 1.
Okay.
BY is 1.
Yep.
Constant is 1.
Okay.
3, RBY is 2.
Okay.
MB 1.
Okay.
Constant 1,000.
Okay.
C.
Yeah, now you have to look look a little bit for them. Okay. What's negative 5,000?
5,000.
Oh.
Yeah.
Oh, okay. Yep.
C2 is 1.
This is 5. C2 is 1. Okay.
Constant is 0.
Okay.
6. RAY is
Okay.
C3 is 2.
Okay.
C4 is 1.
Okay.
Constant is negative 666.6 repeat.
Okay.
7 and RAY is 2.
Okay.
C3 is 1.
All right.
0.
Okay.
8 is C1 is 1.
Okay.
2 is 1.
Okay.
C3 is negative 1.
Okay.
4 negative 1. Constant is 3, 3, 3, 1, 3 repeating.
Okay.
9 C1 1.
Okay.
C3 is negative 1. Constant is 5.
Okay. Thank you. All right. I'm going to turn that on. Internal tension of negative RAX plus 5,000. So that is 2,500. We have a shear force cut 1, cut 2. So shear force is RAY minus 1,000. So that must be 677.5 negative. Right? Did I do that right? And then a bending moment that is, okay, so RAY times X minus 1,000 times X. So RAY is 312 minus 1,000. So I think this is negative 677.5 times X plus 1,000. Okay. And so at X equals 1.5, that's where we're trying to calculate this stress. We have T is equal to 2,500. V is equal to negative 677.5. And M is equal to negative 16.25. Feels like a lot of work for such small values, but you got to be careful. Okay, so now the stress tensor. So first we'll do stress tensor due to internal tension. We got sigma xx is equal to positive 2,500 divided by the cross-sectional area, which is 0.04 times 0.08. And we get 0.78 megapascals. So the stress tensor due to tension is 0.78, zeros everywhere. And now we'll go to the shear force. Okay, so the XY shear stress is negative VQ over IB. Q so the area above the region that we want is 0.02 times 0.04. So that's 0.0008 times 3/8 of 0.08. So that's 0.03. And so that is 2.4 times 10 to the minus 5. And I is 1/12 times the base times the height cubed. (1.706) repeating times 10 to the minus 6. And B is 0.04. So tau xy. Our V is negative 677. So we got a negative of a negative 677.5 times 2.4 times 10 to the minus 5 divided by 1.707, I'll call it, times 10 to the minus 6 divided by 0.04. And that is 0.24 times 10 to the 6 pascals. So the stress tensor due to shear force is 0.24, 0.24, 0.0000 pascals. And I know I'm over now, but this is going to be really fast. So the stress tensor due to bending moment, that's an XX stress. It's equal to negative my over I. The y is positive because we're above the neutral axis. The m, negative 16.25. We got negative of negative 16.25. Y is positive 0.02. And we're dividing by the I, 1.707 times 10 to the minus 6. And you get positive 0.19 times 10 to the 6. And so all together, we get a total stress tensor anywhere along that line that's equal to 0.78 plus 0.19, so that's 0.97. And then 0.24, 0.24, 0. Okay, we did it. Anybody have any questions about that? Okay. So good luck with studying. I have office hours tomorrow from 2 to 3:20. And then Friday is after the test.
So the problem on the test will probably be some similar to this.
Yeah, it probably won't be the whole thing, but they'll definitely, this will be like kind of a focus, working on this stuff. But be sure you're ready for old stuff too. Glance back at those at least. Make sure that you remember. But this incorporates most of the old stuff. I mean, at this point, I could ask for, like, say, the maximum shear stress at that point. You'd have to calculate the principal stresses and then calculate the maximum shear stress from there.
Yeah.
So be ready for that kind of stuff.
On a test though, will you ask for principal stresses?
Oh, you're right. So yeah, I can't do that.
Because I can't do my dumb calculation.
That's true. I could do one that didn't have any shears, then that would be a principal stress tensor, and then I could ask for the maximum shear stress.
Yeah. I guess I could go old school and do my calculate the.
No, I want you to be able to do this with a Hello Kitty calculator, as long as you can program the compliance matrix into it.